3. Today we're going to talk about the multiplicative identity. So in regular math, this is basically the number you multiply it to another number and nothing would happen. So for example, 3 times 1 is equal to 3. Notice how when you multiply by 1, nothing happens. This right here is called the multiplicative identity. Now, it sounds really simple, and you've probably never heard of that because it's such a simple idea. Now, what you didn't know is that concept applies to many worlds of math, and in matrices it also applies. So what we're talking about now is what if you had some matrix, like let's call it 1, 2, 3, 4, and you wanted to multiply something, and you want to get itself back, right? So this is matrix A, and you want to get back to itself, matrix A. Now, a lot of people think it would be 1, 1, 1, 1, but you can quickly see once I put in my rows and columns, that's not going to work, right? Because this is 1 and 2, that's already going to make 3. So there's a really simple way to fix it. All we have to do is erase this and put some zeros in. And look at that. That fixes it, because now I have 1 plus 0, which is 1. This is 0, that's 2, that's 2. 3 plus 0, 3. 0, 4, 4. So this thing, we put I, that's the multiplicative identity in matrices. So you want to highlight this. This is what we're working with. So if I extend that concept further, what we want to do is understand if I have 3 and I multiply it to 1/3, notice how I get back your identity. So 3 times 1/3 is 1. We call these inverses of each other. So 3 and 1/3 are considered inverses, which means in matrix world, if I do A times the inverse of A, that would get back I, or your identity matrix. So let's try it. It says show that B is the multiplicative inverse of A, where A and B are that. So essentially we want to see that if I do A times B, I should get I. That's what we're wondering. So let's see. -1, 3, 2, -5 times 5, 3, 2, and 1. Let's put our lines down. So -5 plus 6, yep, 1. -3 plus 3 is 0. 10 minus 10 is 0. 6 minus 5 is 1. Yep, so it checks out. Now what's really cool about this is had we flipped it around, 5, 3, 2, 1, -1, 3, 2, -5, you're also going to get 1, 0, 0, 1, which means if they're inverses, the commutative property does exist. So you can write the commutative property of multiplication works if they are inverses. That's a cool little tip there. So now let's actually find it. It says find the inverse of that given matrix. So there's a lot of ways of doing it. I'm going to show you the most basic way. So 2, 1, 5, 3, and we want to figure out some matrix, and our goal is to get to 1, 0, 0, 1. The most basic way is to just call it A, B, C, and D, and then figure out the missing variables there. So let's multiply. This would be 2A plus C. This would be 2B plus D. 5A plus 3C. 5B plus 3D. and that's 1, 0, 0, 1. And then we translate that to equations. 2a plus c should be 1, 5a plus 3c should be 0, 2b plus d should equal 0, and 5b plus 3d should equal 1. And then we're not going to solve that here because you guys can all solve a system. You're going to get a equals 3, b equals -1, c is -5, and d is 2. Therefore, a inverse is going to be 3, -1, -5, and 2. And there's your inverse. So that's one way to do it. Basically, you make a system and solve it. There is a faster way, and this is what most people do. There's actually a formula or a definition for this. You do 1 over this. It looks like absolute value. That actually means determinant, and you've actually learned that in Algebra 2 a long time ago, so I have to review that. And then dA negative B negative C. So of course this is assuming that your original is A, B, C, and D. And then you're going to want to put a box around this. That's a formula that most people do because it's really fast. And it looks really hard to remember. And it's really not too bad because you'll notice a couple things here. A and D will switch. So notice that A and D switch. B and C don't move. So put a star. B and C negate. That's a really easy way to remember what happens. A and D will switch. B and C negate. Now the only thing to talk about is this determinant thing. So we do got to talk about that. So if your matrix A is A, B, C, D, the determinant of A, or you'll see it as absolute value A, that simply means AD minus BC. So you basically multiply this diagonal and that diagonal and subtract them. So essentially, that's it. And we'll talk more about this determinant thing next class, but you'll see that for now, we just need the operation. So let's try it. Here's our matrix, -1, -2, 3, 4. So A inverse. I need 1 over the determinant. So that would be -4 minus -6. And then I'm going to switch A and D. So 4, -1, negate B and C. It's 2, -3. And let's do the math now. That'd be 1/2 times 4, -3, 2, -1. Put the 1/2 in, so that's 2, 1, -3 over 2, -1 over 2. So right there is our inverse. Okay, now let's try a direct application of this inverse, because at this point you're probably wondering like, hey, this is really cool, but what's the point of all of this? So here's a system that you can obviously solve in a multitude of ways. I'm going to show you how a matrix can actually be used to solve a system. You can actually convert this to a matrix by taking the coefficients. So -1, -2, 3, and 4. And then we take the variables here. Move this over. Here's your variables, x and y. And then your answers are over here, -5 and 11. And you might be thinking, well, how does that even work? But remember, if you're to multiply, put your row in, there's your column, and look, -x minus 2y, that will equal -5. 3x and 4y, that equals 11. Now at this point, what we're going to do is actually use some matrix algebra. We're going to call this thing A, x, and that equals b. And we're going to solve for x. Now what's really interesting is now we're going to talk about matrix algebra. In matrix algebra, a couple things actually don't exist. There's no division. That's a really huge thing. You can't actually divide, but for the most part, everything else is still there. You just can't really divide. But it's really easy to go around it. Just multiply by a fraction if you have to like divide by 2, for example. But in this example, right, in regular math, you would divide by a. But in matrix land, you multiply by what would cancel a out, which would be a inverse. So what you do is you simply do this, multiply by a inverse. Now, unfortunately, it's not as simple as it looks. Because the second thing to remember is the commutative property of multiplication does not exist, which means you have to take note of the side you're multiplying on. So if I do a inverse on the left, you have to think of it as on the left of everything. So these will cancel, that's nice, and x will equal a inverse times b. And that's how you do it. That might look like really easy, but a lot of people will do this. They do a times x equals b, a inverse, but then they write x equals b times a inverse. This is wrong. Because you'll notice if you look at the inverse, I multiply it to the left here, but because this commutative property doesn't exist, you can't multiply to the right on the side. It's no longer equivalent, which means this thing has to be on the left in order for it to be mathematically true. So that's why this thing doesn't really work. So here's our matrix algebra. So all we need to do to find our matrix X, our answer, is figure out A inverse and multiply it to B. So there's A. Let's find A inverse. So 1 over the determinant, that's -4. Oh, we did that already. Let's erase this. So that's convenient. That's the same matrix as earlier. So we're going to grab this thing. 2, 1, -3 over 2, -1 over 2, and multiply this thing to matrix B. So actually, let me make this a little bit nicer. X equals, this is our A inverse, put that there. Matrix B is -5, 11. Let's put in our dotted lines right there. And let's do the math. So that would be -10 plus 11, that's 1. And this would be -15 over 2, no, positive 15 over 2 minus 11 over 2, which is 4 over 2, which is 2. So 1, 2 is our answer. And look at that, we solved it using matrix algebra. And we can verify 1, 2. Plug in 1 and 2 there, that works. Plug in 1 and 2 there, also works.